China built the world's largest petrochemical complex on an island. Not near an island, not beside one. On one, a remote stretch of land in the East China Sea that had to be partially created before a single pipe could be laid. This facility processes over 800,000 barrels of crude oil every single day. That's enough oil to fill over 127 Olympic swimming pools every 24 hours. You heard that right. And the most extraordinary part isn't the numbers. It's how they pulled it off. Here's where this story begins, with an island you've probably never heard of. Where is this place? Picture the East China Sea, about 18 miles off the coast of Zhejiang province. Scattered across the water is the Zhoushan archipelago, over 1,000 islands, most of them small, rocky, and largely unremarkable. For centuries, this was fishermen's territory, quiet, forgotten by industry, the kind of place that doesn't appear on maps unless you're specifically looking for it. But China was looking very specifically. Tucked within this archipelago is Yushan Island, and this is where everything changes. On its own, Yushan wasn't impressive. It was modest in size, sparsely populated, and surrounded by deep, unforgiving water on all sides. Most planners would have looked at this location and walked away. The logistics alone seemed impossible. You're talking about building one of the most complex industrial facilities on Earth, on an island in the middle of open sea, with no existing infrastructure, no roads in, and no room to grow. But that last problem, the room to grow, turned out to be exactly why China chose it. The deep water surrounding Yushan wasn't an obstacle. It was the entire point. The Zhoushan Strait sits along one of the most heavily trafficked crude oil shipping lanes in Asia. Supertankers, the kind that carry 2 million barrels of oil in a single voyage, can sail directly to this location without the shallow water limitations that cripple other ports. You can't build a refinery of this scale somewhere that can't receive the world's largest ships. Geography made Yushan the only logical answer. And then there was the distance from dense population centers, critical when you're planning a facility that will be running explosive, flammable, and toxic processes around the clock. Yushan gave China the deep water it needed, the separation it required, and the open space it was about to create. But the island as it existed wasn't enough. Not even close. The footprint needed for this complex dwarfed what nature had provided. And that meant, before China could build the world's largest petrochemical base, it first had to build more island. What came next was one of the most ambitious feats of land engineering ever attempted, and it set the foundation for everything that followed. Building the island first. Before a single refinery tower went up, before a single pipeline was laid, China faced a problem that would have stopped most nations cold. There wasn't enough land. The site needed to support thousands of acres of heavy industrial infrastructure, massive processing units, tank farms, pipelines, and port terminals, all of which would generate extraordinary weight, vibration, and thermal stress. And the ground beneath it all? It was going to be made, not found. Land reclamation at this scale is not a construction project. It's a geological act. Hundreds of millions of cubic feet of rock, sand, and fill material were dredged and deposited into the surrounding seabed to expand Yushan's footprint to the size the project demanded. You're not talking about adding a shoreline. You're talking about creating entirely new landmass, flat, stable, and engineered to bear loads that would crush unprepared ground. Every square foot of reclaimed land had to be compacted, stabilized, and tested before it could support the weight of what was coming. But here's where the tension builds. Reclaimed land is notoriously unstable. It settles, it shifts, tidal forces push against it constantly. And when you're planning to place enormous crude distillation towers, structures that can stand over 200 feet tall and weigh tens of thousands of tons on top of that reclaimed ground, a fraction of an inch of uneven settlement can crack welds, misalign pipelines, and trigger catastrophic failures. China's engineers knew this, and they didn't guess their way through it. The foundation work involved driving steel and concrete piles deep into the seabed beneath the reclaimed surface, essentially stitching the new land to the ocean floor below. In some sections, pile depths reached over 100 feet, anchoring the surface above against both settlement and lateral movement from tidal and storm pressure. The sheer volume of foundation work completed before visible construction even began was staggering, and this was just the ground. The island also had to be shaped, not just expanded. Drainage systems, internal road networks, and utility corridors had to be engineered into the reclaimed land from the start because retrofitting them later would be impossible. You were essentially designing an entire city's substructure. Before the city existed, every decision made underground would either support or undermine everything built above it for the next 50 years. When the ground was finally ready, the scale of what was about to be placed on top of it almost defied comprehension. Because building the island was only the foundation of the challenge. What China was about to construct on top of it would become the most complex refining and chemical production system ever assembled in one place. The refining megacomplex. Walk onto this island today, and the first thing that hits you isn't the smell or the noise, it's the scale. Towers stretch into the sky as far as you can see in every direction. Massive cylindrical vessels the size of apartment buildings sit in long ordered rows. Steam rises from dozens of points simultaneously. Flare stacks burn off excess gas in controlled columns of fire that are visible from miles away. This is not a refinery. This is a refining city. The Zhoushan Petrochemical Complex was built in 2 major phases, and each phase alone would have ranked among the largest refinery projects ever completed. Phase 1 brought online a crude oil processing capacity of 400,000 barrels per day. That number is already extraordinary. Most world-class refineries operate in the range of 200 to 300,000 barrels per day. But China wasn't building a world-class refinery. Phase 2 matched Phase 1 barrel for barrel, pushing total capacity to 800,000 barrels per day. Combined, this single facility on a single island processes more crude oil daily than the entire refining capacity of many mid-sized oil-producing nations. You heard that right. And this isn't just about volume. The complexity of what happens inside this facility is what separates it from anything else on Earth. Crude oil arriving at this island doesn't just get distilled and shipped out as fuel. It gets torn apart at a molecular level and rebuilt into hundreds of different products. Crude distillation units separate the raw oil into fractions by boiling point. Fluid catalytic crackers break heavy fractions into lighter, more valuable products. Hydrotreaters strip out sulfur compounds to meet fuel quality standards. Reformers convert naphtha into high-octane gasoline components and chemical feedstocks. Every unit feeds the next in a sequence so tightly integrated that the entire complex operates more like a single living system than a collection of industrial machines. But the tension here is real, because a system this integrated is also a system where a single failure cascades. The interdependency that makes this facility so efficient is also what makes it so demanding to operate. Every unit runs at extreme temperatures and pressures. Every connection point, and there are tens of thousands of them, is a potential failure node. The engineers who designed this system had to build redundancy into every critical pathway while simultaneously minimizing the physical footprint. Because space on a reclaimed island is finite and expensive, in a way it simply isn't on the mainland. What they produced is a facility with almost no wasted space and almost no margin for error. The payoff of that precision is a refinery that doesn't just process crude, it captures value at every single stage of the process. Byproducts that would be waste at a conventional refinery become feedstocks for the chemical plants running alongside the refining units. The economic efficiency of this design is built directly into the physical layout of the island. But moving all of that crude from ship to storage to refinery and doing it at 800,000 barrels a day required something the island didn't yet have. Something that had to be engineered from the water up. And that infrastructure would become an engineering achievement in its own right. The Pipeline City. You can't see them, but they're everywhere. Beneath your feet, above your head, running alongside every road, and threading between every processing unit. Hundreds of miles of pipeline form the true nervous system of this island. Without them, the refinery towers are just expensive steel. It's the pipelines that make the whole system breathe. Crude oil arrives at the port terminals and immediately enters this network. It moves through large-diameter trunk lines into the storage tank farm, then gets pulled from storage into the crude distillation units based on the refinery's processing schedule. From there, Intermediate products, naphtha, gas, oil, residue, branch off into their respective secondary processing units. Finished products flow out toward export terminals or into the petrochemical plants running alongside the refinery. Every barrel of oil that enters this island travels through multiple pipeline segments before it leaves as something else entirely. But here's what most people never consider. Managing flow across a system this large isn't passive. Pressure, temperature, flow rate, and product composition are being monitored and adjusted in real time across thousands of individual pipeline segments simultaneously. A pressure imbalance in one section doesn't stay local, it propagates. An unexpected change in crude composition affects downstream unit performance within hours. The control systems running this pipeline network are as sophisticated as anything in aerospace. And the physical installation of these pipelines on reclaimed land added another layer of complexity. Thermal expansion causes pipelines to grow and contract with temperature changes. On a facility running processes from cryogenic to over 900 degrees Fahrenheit, the expansion tolerances across miles of pipe require carefully engineered expansion loops and flexible joints at every critical junction. Miss one, and the pipeline tears itself apart. The engineers got it right, and the result is a fluid logistics system moving millions of barrels worth of product every single day without interruption. But none of this pipeline infrastructure matters if you can't get the crude onto the island in the first place, and doing that required building a port unlike anything the world had seen. The storage tank farm. Before a single drop of crude enters the refinery, it has to wait. Not because the system is slow, but because the system is strategic. The storage tank farm at Zhoushan Petrochemical isn't just a holding area. It's a buffer, a reserve, and a geopolitical instrument all at once. And when you see it from above, it looks less like an industrial installation and more like a small city of steel cylinders stretching to the horizon. The tank farm holds tens of millions of barrels of crude oil and refined products across hundreds of individual storage tanks. Each large crude tank stands over 60 feet tall and stretches nearly 300 feet in diameter. Step inside one if you could, and you'd be standing in a steel chamber large enough to swallow a professional sports arena. Now multiply that by hundreds. You heard that right. The tanks are grouped by product type: crude segregated from naphtha, gas oil separated from chemical feedstocks, because mixing product grades even slightly can destroy entire processing batches downstream. Each tank is fitted with floating roofs that rise and fall with the liquid level inside, minimizing the vapor space above the product and dramatically reducing evaporation losses and fire risk. Beneath each tank, the reclaimed ground has been reinforced with the same deep pile foundations used across the rest of the island, because a full crude tank exerts pressure on the ground comparable to a multi-story building covering the same footprint. But the tank farm's most important function isn't operational, it's strategic. This volume of storage gives China's energy planners the ability to buy crude aggressively when global oil prices drop, stockpile it here, and feed the refinery at a predetermined cost, regardless of what markets do afterward. It decouples refinery operating costs from spot price volatility in a way that smaller facilities simply cannot. It turns this island into not just a processing hub, but a pricing weapon. That strategic dimension runs through every decision made at this facility, and nowhere is it more visible than in the infrastructure built to bring those millions of barrels to shore in the first place. The deepwater port system. Everything about this island was built around one non-negotiable requirement. The ships had to be able to get here. Not small ships, not medium tankers. The world's largest crude carriers, ultra-large crude carriers, or ULCCs vessels, over a quarter-mile long, carrying up to 3 million barrels of oil in a single voyage and displacing more water than an aircraft carrier. These are the most cost-efficient way to move crude across oceans, and China designed this port specifically to receive them. Most ports in the world can't. The water isn't deep enough, the berths aren't long enough, the loading arms aren't rated for the transfer volumes involved. Building a refinery that can't receive these ships means paying a premium on every single cargo, a cost that compounds into billions over decades of operation. Zhoushan's natural deep water solved the depth problem before construction even began, but the port infrastructure itself still had to be engineered from nothing. The berthing terminals extend out from the island's reclaimed shoreline on massive concrete and steel jetty structures, placing the berth faces in water deep enough to accommodate fully loaded supertankers, depths exceeding 80 feet at the berth face. The mooring systems are designed to hold vessels of over 300,000 deadweight tons against tidal currents and open sea swells. Loading arms, articulated steel structures that connect ship manifolds to the terminal pipelines, are rated for transfer rates of tens of thousands of barrels per hour, allowing a full VLCC to be discharged in under 24 hours. But the engineering tension here runs deep. Open sea terminals face weather conditions that enclosed harbor ports don't. Swells, wind loads, and current shifts all act on a moored supertanker simultaneously, and the mooring system has to absorb all of it without allowing the vessel to drift. A supertanker breaking free at a live crude terminal is not a maintenance problem. It's a catastrophe. The mooring and fendering systems installed here are among the most robust in any commercial port on Earth. The payoff is a port that operates continuously in nearly all weather conditions at a throughput scale that keeps the refinery fed without interruption. But getting crude to the island was only half the infrastructure problem. The other half was connecting this island to the mainland, and that required building something extraordinary above the water, not beneath it. The bridge network. An island refinery, processing 800,000 barrels of crude per day, generates an almost incomprehensible volume of outbound product. Finished fuels, chemical feedstocks, polymers, solvents, all of it has to leave. And before any of it can reach the pipelines, highways, and rail networks of mainland China, it has to cross open water. That's where the bridges come in. The Zhoushan archipelago is connected to the Zhejiang mainland by the Zhoushan Cross-Sea Bridge Network, a series of bridges and causeways spanning over 50 miles of open sea, making it one of the longest ocean crossing road systems in the world. For Zhejiang Petrochemical specifically, this connectivity is the artery that keeps the complex commercially viable. Without it, the island is isolated. With it, the island is plugged directly into China's national logistics grid. The engineering demands of bridging open sea at this scale are severe. Salt air accelerates steel corrosion. Typhoon-force winds apply lateral loads that inland bridges never experience. Tidal fluctuations and ocean currents scour the seabed around bridge foundations continuously. Every element of these structures, from the high-strength concrete mixes used in the pylons to the cable tension profiles of the suspension spans, was designed specifically for a marine environment. Then came the additional challenge of industrial load requirements. These bridges don't just carry passenger vehicles. They carry heavy tanker trucks, loaded with refined products and chemical cargo, running around the clock in both directions. The structural ratings for sustained heavy freight traffic far exceed what a standard highway bridge would require. The payoff of getting this right is seamless connectivity refined products, leaving the island within hours of processing completion, feeding into China's distribution network without bottleneck or delay. But the bridges aren't just logistics infrastructure, they're a statement. They say that this island, once remote, once unremarkable, is now permanently and irrevocably attached to the industrial heart of the world's largest manufacturing economy. And that connection was the entire point from the beginning. China's strategic logic. Nothing about this project happened by accident. Every decision, the location, the scale, the deep water port, the storage capacity, the bridge connections traces back to a single strategic reality that China's energy planners have been working against for decades. China imports over 70% of its crude oil. That dependence runs through shipping lanes China does not control, past choke points that foreign navies can threaten, and through global markets that price oil in a currency China does not issue. For the world's largest manufacturing economy, that is an existential vulnerability. Zhejiang Petrochemical is one of the most direct answers China has ever built to that problem. The deep-water port capability means China can source crude from the widest possible range of suppliers, Middle Eastern, African, South American on the largest, most cost-efficient vessels available, without being constrained by port limitations. The massive storage capacity means China can time its purchases strategically, buying aggressively during price downturns and insulating the refinery's operating costs from market volatility. The integrated chemical production means that crude oil arriving at this island doesn't just become fuel, it becomes the raw material for plastics, synthetic fibers, solvents, and chemical intermediates that feed China's manufacturing sector directly. But the strategic tension goes further than energy security. Global petrochemical markets are shifting. Demand for refined fuels is plateauing in developed economies as electrification accelerates. But demand for petrochemicals, the feedstocks behind every plastic component, every synthetic textile, every industrial chemical, continues to grow. China positioned this facility not just to refine oil for domestic fuel consumption, but to dominate the next phase of petrochemical production as the world's manufacturing base deepens its chemical dependency. This island processes crude at a scale and integration level that most competitors cannot match on cost. That cost advantage translates directly into market share across global chemical supply chains. The payoff of China's strategic logic is a facility that doesn't just serve the present, it was engineered to shape the future of global energy and chemical markets for the next 50 years. And when you stand back and look at everything built on this island, the reclaimed land, the refining towers, the tank farms, the port, the bridges, you realize this was never just a construction project. The engine beneath everything. Come back to that island one more time. You're standing on ground that didn't fully exist 30 years ago. Beneath your feet is reclaimed seabed, held in place by thousands of concrete piles driven into the ocean floor. Around you, refining towers process more crude in a single day than most countries consume in a week. Storage tanks hold enough oil to fuel a nation. Pipelines carry product in every direction simultaneously. Supertankers, the length of city blocks, are unloading at berths, engineered to hold them against open sea swells. And behind you, a bridge network stretches across 50 miles of open water, connecting all of it to the mainland. This is not an industrial facility that China built to keep the lights on. Every barrel processed here feeds a manufacturing economy that produces everything the modern world consumes. Electronics, textiles, automobiles, pharmaceuticals, packaging, construction materials. The petrochemicals leaving this island don't just become fuel, they become the physical material of global commerce. And China built the capacity to produce them at a scale and a cost that no competitor on Earth can currently match. But here's what makes this island truly staggering. It isn't finished. Expansion phases are already in planning. The reclaimed land has room. The port can handle more ships. The pipeline network was overbuilt, deliberately engineered for a throughput capacity beyond what the current facility demands, because the engineers who designed this place weren't building for today. They were building for 50 years from now. China didn't just construct the world's largest petrochemical base on an island. It built the physical foundation of its industrial future and anchored it to the ocean floor so nothing could move it.